Earth. As far as we know, it's the only home to life in the universe. Why? What is it that makes our planet so special? The answers are hidden deep in the Earth's past. To find them, we must travel back in time, to see the first humans walk the Earth, to ride continents on a collision course, face killer dinosaurs, dive into oceans full of bizarre life forms, feel the bitter chill of global ice ages, and experience the fury of cosmic missile attacks. We must travel back in time until we reach the birth of the Earth itself. Then we can piece together our planet's incredible story and discover why all of this...
You may not recognise it, but this is our planet in its very earliest days. Little more than a few pieces of rock colliding as they circle the sun. These impacts were so violent they generated immense amounts of heat. And they also delivered vast quantities of radioactive material to the Earth. Eventually, when the outer layers of the planet cooled, these two powerful sources of heat were trapped in a huge hot core. The centre of our planet is as hot as the surface of the sun. This is the source of Earth's vast heat energy. And it's what fuels volcanoes to this day. Trapped within our planet, Earth's hot core has been continuously releasing unimaginable amounts of heat. It gives you some idea how much when you realise that even after 4.5 billion years, there's still plenty left. Earth's inner heat makes the planet's surface incredibly dynamic. It has created a restless, continually changing landscape unlike any other in the solar system. It's a world of destruction and renewal.
We, our spaceship. Welcome aboard for our one-year cruise around the sun. Yes, we do revolve around the sun, but not on a circle, on an ellipse. and it's now, during the first days of January, that we're closest to the sun. So why is the weather so cold? In fact, the difference between near the sun and far from the sun is insignificant. There's a much more important reason. The Earth doesn't spin straight, but slightly askew. The axis isn't vertical, it's tilted on its orbit. So when the northern hemisphere tips into shadow, the nights are long, the days are short. But more importantly, because the Earth is tilted, the sun's rays reach us at different angles. In the tropics, a ray of sunlight hits the ground vertically. It's hot. But the same ray in the northern hemisphere arrives at an angle. Its energy is spread over a surface 3 times greater, providing 3 times less heat. We're cold. In the north, it's winter. In the south, it's summer. The tilt of the Earth's axis gives us the seasons. At this very moment, you're hurtling through space at 107,000 kilometers an hour. That's 30 kilometers every second. The Earth takes a year to go around the sun. And along with the Earth, 8 other planets circle the sun, each on its own orbit. On the orbit just next to ours is our neighbor, Venus. Venus travels faster than the Earth, overtaking us. It's the brightest planet, the one we see best. Sometimes in the evening, sometimes in the morning. Why in the morning? We see Venus to the right of the sun. Seen from the Earth, this is what happens in the morning. We're looking at the part of the sky where Venus is. It appears on the horizon well before the sun, while it's still dark and the sun is still below the horizon to the left. That's why, in this position, we see Venus in the morning, at dawn. As the Earth continues to turn, we see the sun. It lights up the sky until we can't see the stars or planets anymore. So we continue our voyage on board our planet Earth. On the next orbit to the left, the Earth has a faster-moving neighbor, traveling at 125,000 kilometers per hour and overtaking us. This is Venus. We call it the morning star, but it's not a star, it's a planet. What's the difference between a planet and a star? They look the same, but the stars shine like our sun. The planets don't shine, they reflect the sun's light. They're part of our solar system and are near to us. The stars are very far away. We can't reach them. This is Sirius, next to Orion, one of the closest stars. Even such a close star is out of our reach. If our spaceship Earth left its orbit and headed out of the solar system towards Sirius at its normal cruising speed, we'd take 80,000 years to get there. While at the same pace, we'd reach Venus in just 16 days. 80,000 years for Sirius, 16 days for Venus. That's the difference between the far-off universe of stars and our solar system with its nearby planets.
So, gradually the Earth cooled down and the surface formed a thin crust. But inside the Earth, hot rock continued to swirl about, moving the crust from below and breaking it apart. This process is called plate tectonics and is happening right now. We'll make a whole video about it in the future. For now, let's just say that the crust of Earth consists of separate giant plates that move around. As they meet, they crumble and create mighty mountains, or violently plunge back down deeper into Earth, creating deep trenches. That's the way the highest place on Earth was formed, Mount Everest, and the deepest, the Mariana Trench. From our perspective, Earth's mountains and trenches are mighty indeed, but when you look at the Earth in cross-section, you can see how tiny they actually are. The part we stand on is the crust, which is about 50 kilometers thick, though it can vary between 5 and 70 kilometers. By the way, the deepest hole ever drilled by man is 12.262 kilometers deep. After the crust comes the mantle. It's a silicate rocky shell and about 2,900 kilometers thick. The mantle consists of the upper mantle and the lower mantle. The upper mantle has different regions too. Its upper part, which is viscous and carries the crust, is called the lithosphere. After that, there comes the asthenosphere, which consists of less mobile, mostly solid material. The lower mantle reaches deep down to the outer core of Earth. Earth's outer core is a liquid layer of iron and nickel about 2,266 kilometers thick. Temperatures vary from 4,000 degrees Celsius to 5,700 degrees Celsius. And in the center is the inner core. It's mostly solid, a ball made of an iron-nickel alloy with a radius of about 1,200 kilometers, 70% the size of the Moon and about the temperature of the surface of the Sun. It is slowly growing at an estimated rate of about 1 millimeter per year. Now for some perspective. This small layer of crystallized melt products of former molten mantle is where we live. Then there's Earth's magnetic field. It's an invisible phenomenon that diverts high-energy particles coming from the Sun and other sources, allowing for a stable environment with comparatively little radiation impact on Earth. But why is it there? Actually, we don't really know a terrible lot about that. We know it has something to do with the core of the Earth. Inside this metal sphere, large electrical currents flow in complicated patterns. They cause a magnetic field that sort of stabilizes itself according to the laws of electrodynamics. This entire system is called the dynamo. But don't let us fool you into thinking we have it all figured out. Speaking of breathtaking information, what about the airy stuff that surrounds us? By volume, dry air consists mostly of nitrogen, oxygen, argon, carbon, a variable amount of water vapor, and small amounts of other gases. Humans are very dependent on the lowest layer of the atmosphere, the troposphere, where the weather is. It's 12 kilometers thick on average. Above that is the stratosphere, which is where the ozone layer protects us from the sun's most aggressive type of light. Above that is the mesosphere, the coldest place on Earth, with an average temperature around minus 85 degrees Celsius. At about 80 kilometers up, the thermosphere starts. The transition to space is a fluent one without clear borders, but humans decided that space starts here. At about 100 kilometers, Earth stops and space begins, though the atmosphere extends a bit further. In this region we find the ionosphere, the aurora borealis, and the ISS. And the outermost layer is the exosphere, stretching up to 10,000 kilometers. It merges fluently with outer space where there's no atmosphere at all. The atoms and molecules in this area are so far apart that they can travel hundreds of